in this video lesson, we're going to look at double displacement reactions. So we'll start like the others and define what a double displacement reaction is and look at the general equation. So a double displacement reaction is a reaction in which two compounds react to form two new compounds where the cations, which are the positively charged ions, so positive ions, have switched places. Our general equation is AB, so that's the first compound, plus CD, which is the second compound, react and rearrange, and the positive halves, or the front half, of the two compounds are going to swap places to form CB plus AD. So the cations are the positively charged halves of the compound, which will always be written first. They will be the metals or hydrogen. And then they're going to swap partners in terms of the second half of the compound is the negative half, so the anion, which are the non-metals or polyatomic ions, so that they're paired up with new things. We want to make sure that each new compound still contains one cation and one anion, so one positive half and one negative half. There's also some special rules to consider when you're looking at double displacement reactions in terms of how you tell the state of your new compounds. So mostly we look at double displacement reactions as being between two aqueous compounds, and then when we form two new compounds, sometimes they're both aqueous and sometimes one of them will be a solid, which is called a precipitate, which is an indicator of a reaction happening. So you'll see this table we have on the back of your periodic table, and I'm going to show you how to use it to determine the solubility, or whether your compound is going to be aqueous, so soluble, or solid, insoluble. So here the word soluble, means that it's aqueous, it dissolves in water. Insoluble means that it does not dissolve in water, and it would be a solid. So in the top half here, these are compounds that are going to be aqueous. So soluble ionic compounds contain these different anions. So everything that falls in here, for the most part, are going to have the subscript aqueous, with the exceptions, these ones, meaning that they'll be solids. So any compound containing these anions is usually aqueous, but there's a few exceptions here. And the bottom half of the table works in the exact opposite way. Any compound containing these anions is generally going to be a solid, so insoluble, but there are a few exceptions here which will be aqueous. So we'll do a few practice questions to see if we can practice using that. So the first practice question here, we've got lead nitrate and potassium iodide. So lead should have a Roman numeral here. Let's say it's lead 2. That should be added in there. My apologies. So that would give us Pb2+. Nitrate is a polyatomic ion, so NO3 1-. We crisscross. That's going to give us PbNO3 2. We can check lead nitrate using our rules. So the second half, the anion half of this compound, is nitrate. Nitrate is in the list of soluble anions, and there are no exceptions, which means that this is going to be aqueous. Next compound is potassium iodide. Potassium is K plus, iodide is I minus. We crisscross, that's going to give us Ki. We can check our solubility rules. Iodide is this ion here, and it is normally aqueous. It's paired up with potassium. Potassium is not one of the three exceptions, which means that it is going to be soluble or aqueous. I often find that it's easier to predict the products using the formulas rather than the word equations, and then I'll write the word equation after. So our two positive halves here, the cations, are the potassium, K plus, and the lead, 2 plus. So these are now going to switch places. We're going to form lead iodide, so PbI2. So we're still swapping. So the 2 and the 1 are swapping to get us the 2 bottom there. And then we're going to have potassium pairing up with the nitrate. So that's going to be KNO3. We should determine our solubility. So lead iodide, so PbI2. I is here. We look at the exceptions. Lead 2 plus is one of the exceptions, which means it's going to be a solid. So this is going to form a precipitate. The KNO3, NO3 has no exceptions, so the KNO3 is going to be aqueous. Now we need to write out our word equation and then balance our reaction equation. So here we've got lead 2 iodide, giving the name of that compound, and then plus potassium nitrate, which is the name of that compound. Finally, to balance this, if we look over here, we have 2 nitrates, and over here we only have 1. So we can add a 2 out in front of that. That gives us 2 nitrates is balanced, but it gives us 2 potassium ions. Here we have 2 iodine ions, so we need 2 of each of these. So we'll add a coefficient 2 in front of the potassium iodide. And then that one's all done. The next example, we've got aluminum nitrate and sodium hydroxide. So ammonium nitrate, ammonium is a polyatomic ion, it's NH4 plus. Nitrate is NO3 1 minus, so when we crisscross, it's a 1-to-1 ratio, giving us NH4NO3. Nitrate, you'll start to see a bit of a pattern here. Nitrate is aqueous, and there's no exceptions, which means that this is going to be aqueous. Sodium hydroxide, sodium is Na plus. Hydroxide is a polyatomic ion, OH minus. Crisscross, and we get a 1-to-1 ratio, so NaOH. Hydroxide is here. It's on the list of usually insoluble ionic compounds, but if you look at the list here, any alkali metal, so alkali are the group 1. So this is group 1 metals. So that's lithium, sodium, potassium, and so on, down that first column of the periodic table. It's an exception. So if hydroxide is paired up with anything on this list, it's then aqueous. Sodium is one of those exceptions. So sodium hydroxide is aqueous. To predict what our products are going to be, we're going to take the 2 positive halves, so the sodium and the ammonium, and they're going to switch places, swap partners, and give us ammonium hydroxide and sodium nitrate. So ammonium NH4OH. So these are all charges of 1. So when we swap them, it's still a 1-to-1 ratio. And then NaNO3, so sodium nitrate. Ammonium hydroxide. Ammonium is one of the exceptions to the solid hydroxide rule, which means it's going to be aqueous. And as we've said a few times already, the nitrates are always aqueous and there are no exceptions, which means that this is also going to be aqueous. This reaction is already balanced, so the only thing we have left to do is to finish the word equation. So ammonium nitrate and sodium hydroxide, making, this is ammonium hydroxide here. Plus sodium nitrate. We have one final reaction. We're looking at hydrochloric acid reacting with potassium hydroxide. This is a little bit of a special case. When you have an acid reacting with a base, it's called a neutralization reaction. Okay, so here's the acid. This is a base because it contains a metal and hydroxide. But regardless of the fact that it's specifically a neutralization reaction, it still follows the same double displacement rules. So hydrochloric acid, hydro tells you that it's what we call a binary acid. It only has two elements in it, so hydrogen and chlorine in this case. So hydrochloric acid is HCl. Cl is one of the ions that's usually aqueous. Hydrogen is not an exception, so going to be aqueous. All acids and bases are aqueous. Potassium hydroxide, potassium is K plus, hydroxide is OH minus, so we're going to get KOH. Hydroxide is normally a solid, but potassium is an alkali group 1 metal, so that's one of the exceptions, which means it's going to be aqueous. We're going to crisscross, or not crisscross, but we're going to swap our hydrogen and our potassium. So these are the positive halves of these compounds, so hydrogen and potassium, to give us potassium chloride. So we're going to get KCl. Again, Cl is part of the aqueous group, and potassium is not an exception. So this is going to be aqueous. Plus HOH, okay, which we can write out as water, so just H2O. If you find it easier to see it in terms of the double displacement as HOH, then you can write that, that's okay, I don't mind. Or you can write it as H2O. Neutralization reactions, when you have an acid and a base, will always produce water, so this H2O. And H2O, water, is always a pure liquid. When we give the name for this, this is potassium chloride. So our word equation, potassium chloride plus water. If you want to call it dihydrogen monoxide, that's fine, but water is absolutely acceptable anytime you're naming water. So that's a kind of look at that. We're going to do a little lab activity where you're going to explore the solubility rules a little bit more, and there's some practice questions on the back and in the textbook to do in class.